So the paper's MemHarness. Memory is reconstructed, not replayed. It's authored by Rong Wu and a team from Zhejiang University, Shanghai AI Lab, and a few other institutions.
Yeah, and if you're building LLM agents right now, this is basically the 60-second TLDR of why your memory-augmented agent is probably failing in production.
Exactly. It's just blindly copy-pasting past trajectories into its current context. Like this verbatim replay causes catastrophic negative transfer the second your agent's environment changes.
Right, and MemHarness completely overhauls this by looking at human cognitive science. So instead of just pulling a memory from a vector database and replaying it, the model retrieves it, actually critiques it against the current state, and then reconstructs it to fit the exact situation before doing anything.
Which is wild. Built on a Qwen 2.57b instruct backbone and trained entirely end-to-end with group relative policy optimization, or GRPO, it learns this reconstructive reasoning purely as a latent skill.
Yeah, and the result is this 7 billion parameter model just massively outperforms standard RL baselines and even giant closed-source models like GPT-4o on complex benchmarks, like ALFWorld and WebShop.
And the benchmark numbers are impressive, but the most mind-bending finding here isn't just that the reconstructed memory makes the agent better at a specific task.
Oh, not at all. The real breakthrough is that training the model to critique and reconstruct its memories intrinsically improves its base reasoning capabilities.
Wait, so you can turn the memory bank completely off at inference time?
Yeah. You turn it off, and the model is still a vastly superior thinker simply because of how the training process basically rewired its internal weights.
Wow. We're definitely going to dig deep into that intrinsic improvement today, because figuring out how these architecture shifts actually rewire model behavior is, well, exactly what we do here on AI Paperslope.
Exactly. So if you're working with RAG or memory-backed agents, the core problem this paper identifies is this thing called the applicability gap.
Right, the applicability gap.
Yeah, so the current paradigm for memory-augmented agents, and we're talking about popular methods like React, Expel, or MemZero, they rely really heavily on semantic similarity.
Which means the standard flow is an agent maps out its current task, queries a vector DB for a semantically similar past memory, and just, shoves that raw memory straight into the prompt.
Right, but the fatal flaw here is that interactive decision-making environments are POMDPs, partially observable Markov decision processes.
For those of you who might be a bit rusty on POMDPs, it basically just means the agent doesn't have a god's eye view of the world. It's like walking through a foggy room.
Yeah, it only sees the immediate observations right in front of it at any given time step.
Which means a memory might be perfectly semantically relevant to the overall task, but practically toxic because the agent's current concrete state doesn't match the historical state where that memory was formed.
Exactly. The abstract goal is the same, but the local variables are totally different.
It's like software development, right? Relying on verbatim memory replay is like a developer grabbing a highly upvoted Stack Overflow snippet from, 2018 and pasting it directly into a 2026 code base.
Oh, that is a perfect analogy, yeah.
The code is entirely relevant to the semantic problem they're trying to solve. But the specific dependencies, the versioning, the architecture, the state of the environment have fundamentally changed.
So the developer doesn't solve the problem, they actively break the build.
Exactly, they break the build.
And conflating semantic relevance with action-level applicability is the exact trap traditional agents fall into. The researchers realized that, human memory just does not function this way at all.
Right. They anchor this architecture in cognitive science, specifically foundational psychological work by researchers like Loftus and Palmer.
Yeah, because human memory is not a video recording stored on a hard drive that you just hit play on.
Yeah.
It is highly reconstructive.
When you recall a past event, your brain actively reorganizes that past experience using present cues and current context.
And MemHarness basically takes that psychological concept and operationalizes it into a superstructured 5-stage pipeline for AI agents.
Okay, let's break that down. So instead of just retrieve, read, react, the agent cycles through environment observation, memory retrieval, memory critique, contextual reconstruction, and finally, action generation.
Right, so let's actually walk through what an inference pass looks like under the hood here.
Yeah, please.
So the agent maintains an explicit memory bank using a Milvus vector database and BGE M3 embeddings. and it maintains a rolling history window of its current environment.
They use a window size of 3, right? So it's always looking at its last 3 steps.
Exactly, window size of 3. If the agent decides it's stuck and needs help, it triggers a query and pulls the top 3 most relevant past experiences.
And here is where the architecture completely diverges from the old paradigm. Because instead of feeding those top 3 raw memories directly to the action generator, the policy model enters a dedicated critique and reconstruct phase.
Right, it takes the overall task description, the current history window of 3 steps, and the retrieved memory.
And the crucial engineering detail here is that the retrieved memory isn't just a summary. It includes the original historical source observation, right?
Yes, the policy model is forced to sit there and compare the historical state against the current state, identify exactly what variables have changed, and generate state-specific updated guidance.
So it's essentially rewriting its own memory, so it actually applies to the literal room it's currently standing in.
Exactly, it rewrites the memory.
Okay, I have to push back on the mechanics of that, though. Because it sounds like a massive recipe for hallucination.
How so?
Well, if the vector database returns a memory that is just completely useless for the current state, like, say the agent is trying to buy a television on an e-commerce site, and the database returns a memory about buying a coffee maker.
Right.
Doesn't forcing the agent to reconstruct that memory just make it desperately try to invent a connection that isn't there?
It totally would, if it were forced to use it. But MemHarness has a learned escape hatch built in.
Oh, interesting. What kind of escape hatch?
So during training, the model is taught that if a memory cannot be logically adapted to the current state, it must output a specific token, which is the MPTY token.
Okay, so just angle brackets, MTTY.
Exactly. And when the system's parsing logic sees that MPTY token, it intercepts the process and triggers something called self.
That's self. So that's like a fallback instruction.
Yeah, it's a systemic override. It basically tells the agent, hey, no validated historical principle applies to this specific moment. So ignore the database and rely entirely on your own immediate observation and self-reasoning.
That is so smart.
Right. And the brilliance is that the exact same policy model is handling all of this. It either outputs the reconstructed guidance or it outputs self, and then that resulting context is passed to the final action generation step.
The elegance of that pipeline is clear. But as anyone who has tried to train a complex reasoning model knows, this raises a massive technical red flag.
Oh, the training data problem.
Yeah. How on earth do you train a model to do this? There is no ground truth human data set for how to perfectly reconstruct an abstract memory for an agent navigating a digital environment.
No, there definitely isn't. You cannot use supervised fine-tuning or SFT because you don't have human labelers writing out the perfect internal monologue comparing historical state A to current state B.
Right. SFT is a complete dead end for this specific problem. You can't just script human cognitive processes into training data for a digital agent.
Exactly. So the researchers bypass this bottleneck entirely by turning to group relative policy optimization, GRPO.
Ah, GRPO. That is the mechanism that makes the entire MemHarness framework possible.
Yeah, because the reconstructed guidance is essentially a latent variable-like an internal thought process without explicit human supervision.
So they train the entire retrieve, reconstruct, act pipeline end-to-end using reinforcement learning. And it's driven purely by task outcomes, right?
Right. If you're an ML engineer listening to this, the GRPO parameters they used are fascinating. For every single prompt in the training phase, they sample a group of 8 different trajectories.
Okay, 8 trajectories. And the reward signal they use is incredibly sparse and almost entirely outcome-driven.
Yeah, the agent gets 10 points for successfully completing the task and 0 points for failure. That's it for the task reward.
Wow, just 10 or 0. Though they do add one tiny formatting bonus, weighted at just 0.1, right?
Right. This micro reward is just to enforce the structural protocol. The agent gets this fraction of a point if it sticks strictly to the exact XML tags like think, retrieve memory, and action, and if it outputs its thoughts strictly in English.
So how does that actually teach it to reason?
Well, the magic of GRPO lies in the credit assignment. Standard RL really struggles with long horizon tasks because it has a hard time associating a long, complex chain of reasoning steps with a final binary outcome.
But GRPO computes a group normalized advantage.
Exactly. By looking at those 8 trajectories sampled for a single prompt, it can clearly see which variations succeeded and which failed. It then assigns a trajectory-level advantage to all the tokens within a successful trajectory.
So it's optimizing purely for final task success. But in doing so, The model is implicitly learning a highly discriminative, latent reasoning strategy.
Yeah, nobody had to tell the Quen 2.5 model how to rewrite a memory. It just figured out through trial and error that rewriting misleading memories, closing that gap between past and present, resulted in that plus 10 reward at the very end of the episode.
That is incredible. The agent is functionally evolving its own internal logic for memory critique. It learns to isolate variables.
Yeah, it figures out that if the historical memory says open the fridge, but the current state observation shows the fridge is already open, it needs to modify the memory to say examine the contents of the fridge.
Right. It learns this purely because trajectories where it blindly copied open the fridge failed and got 0 reward, while trajectories where it generated the critique and modified the action succeeded.
Spot on. And the empirical results really validate how powerful this latent learning is. Let's look at the benchmarks, because for a 7 billion parameter model, these numbers are frankly staggering.
They really are. So they tested the framework on 2 primary environments. First is ALFWorld, which is a text-based simulation of embodied household tasks. Things like finding a specific object, cleaning it, putting it on a surface.
Right. And the second is WebShop, which is this massively complex e-commerce simulation with over 1 million distinct products and highly variable user constraints.
And MemHarness achieved an 85.2% success rate on ALFWorld and 75.6% on WebShop.
Now, put those numbers next to Gemini 2.5 Pro. Gemini scored 62.1% on ALFWorld and just 35.9% on WebShop.
Oh, completely. So the 7B MemHarness model is absolutely crushing a frontier-class closed-source giant in these specific interactive environments.
Oh, completely. It also easily dismantled all the traditional RL-based memory methods they tested against.
But the benchmark scores are really only half the story here. If you look at the ablation studies in the paper, that is where the architecture really proves itself.
Yeah, the ablations are fascinating. The researchers wanted to isolate the value of the reconstruction phase. So they took their RL-trained agent, allowed it to retrieve memories from the DB, but forced it to inject the raw memory directly into the prompt without critiquing it.
Basically forcing it back into the old verbatim replay style.
Exactly. And on ALFWorld, the performance of the agent using verbatim replay actually dropped below the baseline performance of an RL agent that didn't have access to memory at all.
Wait, really? So verbatim replay wasn't just slightly suboptimal, it was actively detrimental?
Yeah, actively harmful. It injects hallucinated variables or outdated constraints into the prompt and completely confuses the action generator.
Which brings us to the aha moment of the entire paper, I think. The most fascinating ablation test is the without memory setup.
Oh, this is the best part.
They took the fully trained MemHarness agent, and at test time, they completely disabled the memory retrieval system. They disconnected the vector database entirely.
No past experiences were available. The agent was forced to navigate the environment, relying purely on its base weights.
And it still scored 83.0% on ALFWorld.
Yeah. Compare that to a standard GRPO trained agent without the MemHarness architecture, which only scored 76.4%.
So by forcing the model to critique and reconstruct memories during the training phase, you aren't just teaching it a parlor trick for handling database queries.
No, the objective of reconstructing memory acts as incredibly high-quality latent guidance. It literally forces the model's internal weights to constantly practice comparing states, isolating variables, and deducing causality.
That rigorous process fundamentally rewires the agent's base reasoning skills. It becomes a sharper, more logical thinker overall, even when it is stripped of its tools and left entirely on its own.
Exactly.
But as technical practitioners, when we see a model supposedly learning deep causality and variable isolation, I think the immediate skeptical question has to be, how do we actually know the model is comparing the historical state to the current state?
Right. How do we know it hasn't just learned a really fancy superficial text completion trick based on formatting artifacts?
Yeah, exactly.
Well, the researchers knew that critique was coming, so they designed a genuinely brilliant counterfactual probe experiment to prove the mechanism.
Okay, how did they do that?
They generated 2,000 offline probes using GPT 5.1. They started with a real successful interaction state where a retrieved memory perfectly matched the environment and was highly applicable.
Okay.
Then they used GPT 5.1 to make a single minimal factual edit to that state observation so that the memory shouldn't work anymore. And they fed both versions to MemHarness to see if its reconstruction module could actually spot the subtle difference.
To make this concrete for you listening, let's look at a specific example from the ALFWorld environment. Imagine the retrieved memory advises the agent. If you can't find a mug in the cabinets, shift your search to open surfaces like the countertop. In the original unmodified state, the agent's observation is looking at an empty drawer, So the agent correctly adopts the memory and plans to keep searching. But in the counterfactual edit, the state observation is tweaked just slightly to say, you see a mug.
And the physical layout of the text, the formatting, the general token distribution, it's almost identical. If the model is just doing superficial pattern matching based on the XML format, it will blindly output the same instruction to go look at the countertop.
But MemHarness doesn't do that.
No, it instantly recognizes that the core premise of the memory, which is failing to find a mug, has been broken by the current state observation.
Right.
It shifts its output to the MTY token, entirely rejecting the historical memory.
Which allows the action generator to just pick up the mug right in front of it.
Exactly. And the counterfactual probe they ran on the WebShop environment is even more impressive because e-commerce observations are incredibly noisy walls of text.
Right, tons of clutter.
Yeah, so the user's initial pass constraint might be to find a product for under $50. The retrieve memory advises the agent. If the product attributes match the constraint, click Buy Now.
Okay.
In the edited state, GPT 5.1 simply changes the price of the product displayed on the screen from $19.99 to $59.99.
Wow, just changing a few characters in the middle of a massive HTML-style text block.
Yeah, and MemHarness zeroes in on the constraint violation, rejects the memory by outputting MPDay, and actively prevents the agent from making a bad purchase.
That deep comparative filtering behavior is exactly why MemHarness is uniquely robust in out-of-distribution or ODE scenarios.
Right. They tested the agent in ALFWorld rooms with completely unseen layouts and entirely new object placements.
And standard raw memory agents fail miserably in ODE testing because a raw memory might reference interacting with a coffee table or a credit card that literally does not exist in the new room layout.
Yeah, the raw memory agent will blindly hallucinate those objects into its immediate environment and try to interact with them, which instantly breaks the run.
But MemHarness dynamically filters out those mismatched entities during the critique phase. It safely extracts the abstract strategy like search horizontally before searching vertically without hallucinating the concrete details of the past room into the present room.
Exactly. And seeing how the agent avoids those ODE traps brings us to how the agent's brain really evolved over the course of the training run.
Right, because they tracked the internal memory decisions over the 150 training steps. And the telemetry shows that the agent didn't just learn one monolithic rule for how to use memory.
No, it learned highly task-specific strategies tailored to the exact environment it was deployed in.
The contrast in behavior between the two environments is striking. Like in ALFWorld, the physical rules of the household are relatively consistent, right? Gravity works the same way, drawers open the same way.
Yeah, and as the agent trained, it developed what you could call a sparse policy. It actually dropped its reliance on memory retrieval down to just 2 or 3 queries per trajectory.
Because the environment's rules were consistent, the agent internalized the physics of the world directly into its parametric weights. It simply didn't need to look up historical advice as often.
Exactly. But WebShop caused the agent to evolve in the exact opposite direction. E-commerce is highly variable. Every single product page is different. The user constraints change constantly. The layouts shift.
So in WebShop, the agent maintained a very high frequency of memory retrieval throughout the entire training process.
But it simultaneously developed an extremely high rejection rate. It became an incredibly picky consumer of its own memories.
It was constantly pinging the vector database for ideas, but aggressively using that METY token to filter out anything that wasn't a perfect logical fit for the specific product page it was looking at.
And across both of those completely different environments, the data shows a direct correlation to task success. The trajectories where the agent actively generated a critique and accepted a reconstructed memory consistently achieve the highest success rates.
Which proves the model wasn't just randomly rolling the dice on accepting or rejecting data. It genuinely learned when to trust its own adaptations and when to rely on its base reasoning.
Absolutely.
So if you're building AI systems, the core takeaway from MemHarness represents a profound shift in how we approach agent architecture. The industry has spent so much time and compute trying to build perfect vector databases, perfect chunking strategies, and perfect retrieval algorithms.
Yeah, we've basically treated memory as a storage problem.
Right. But this paper proves that for AI agents, just like for human beings, having a perfect, indelible memory is largely useless. What actually matters is having an architecture that knows how to critically interpret that memory for the specific, messy reality you're currently standing in.
Well said. Which actually leaves us with a truly fascinating, slightly provocative question about the future of model training.
Well, let's hear it.
We just walked through how end-to-end RL can teach a relatively small 7 billion parameter model to autonomously critique and rewrite its own memories as a latent skill, entirely without human labels, right? We also know this process intrinsically improves the base model. So what happens when labs scale this mechanism up to frontier models?
Oh, wow.
If models inherently improve their base reasoning by practicing this internal reconstruction, it is entirely possible that future open-ended models will start intentionally constructing synthetic memories during their training.
Wait, so they wouldn't be storing real records of things they actually did?
Exactly. They would be generating highly optimized fictional scenarios specifically designed to act as perfectly compressible latent rules to guide their future selves.
Designing optimized fictional memories for a future state that hasn't even happened yet. That is a wild thought to leave you with. Thanks for joining us for this deep dive into MemHarness on AI paper slop, and we will catch you on the next one.